Okay, so let's get going. So today we're mostly going to talk about backpropagation, which is very important and relevant for your first assignment. And also we'll get into a sort of first overview of convolutional networks and the convolution operation. So first, quickly from last time, we talked about optimization using gradient methods. So the deep network is high-dimensional parameterized function, and it has as its output typically just some scalar loss, which we're trying to minimize. So we take gradient-based steps, so we figure out for that high-dimensional function which directions cause it to decrease, and we take steps in those directions. And that eventually, by taking lots of steps, gets us to at least a local optimum. In order to do that reasonably quickly, because we often have very large data sets, we break the data set up into mini batches. So that gives us noisy steps, but by taking many more steps, we can average out the variance and still get to the solution relatively quickly. And in fact, there's some benefits empirically to having the noise in the sense that it explores the loss landscape a bit better. And we talked about several methods for trying to accelerate beyond the naive stochastic gradient. Basically, they were in two classes. Either they did momentum-based acceleration using a moving average of previous gradients, or they did some kind of coordinate scaling, which is true of the last three, where they instead accumulate squared gradients over time and kind of normalize by the square root of that mean squared gradient. And that has the effect not quite of making the loss landscape circular, but making it of equal extent along its coordinates. And in many cases, that can help dramatically in accelerating the convergence and the reducing the loss. Now, because there are advantages of having high learning rates or high steps, large steps in terms of jumping around and exploring the landscape, you still end up with too much energy to really converge to a very deep optimum. So typically people decay the learning rate over time to get to a true minimum of loss. So here you can see validation accuracy for the AlexNet from 2012. You see there's quite big jumps. The red curve is the validation accuracy, and there's quite big jumps in performance when you reduce the learning rate. Alpha is the learning rate, starts off at 0.01. If you instead tried to run the learning rate at, say, 0.001 or 0001, it would learn a lot more slowly and actually not reach the same asymptotic performance at the end. Yeah, question?
Are the level shifts commonly this abrupt, like a factor of 10 in one step? Or?
Yeah, it's pretty common for convolutional networks, yeah. But in some networks, it's quite harmful, such as the transformer networks that we look at later on. Those steps actually cause the model to move away from a current optimum. They kind of bias it away. So in fact, for those networks, people end up using a continuous decay. The difficulty with the continuous decay is it's harder to get right with the steps. You can see that it's saturated, then it's logical to apply a decay manually. If you're looking at the loss curve, it's obvious where it stopped improving, so you apply a step there. Whereas with continuous gradient, you don't have that sort of clarity of when to step. Okay, so because we have two different modes of projects, there are going to be two different handouts and assignments for the project proposal. If you're in 282A, because it's an open-ended project, you have to choose data sources, evaluation metrics, approach, and so on. We want those sort of started earlier, so that handout is out now. You have a couple of weeks to form a team and sort of clarify those aspects of the project so you can get started. The 182 projects are much shorter. The proposal is not much of a proposal because you're given one of the several projects. So we'll just want you to choose among the available choices and form a team. So that handout will be going out next week, and it'll be a shorter cycle for you to get going. Any questions about projects? Yeah?
Oh, just a question about the previous learning rate scheduling.
Yeah.
For example, for transformer,
yeah.
the learning rate decay by a poke or by training step?
I'm sorry, what were the last two?
By a poke or training step? Like every step in a poke, I guess.
Well, let's see. What does it actually do? I mean, it decays continuously, so it's really decaying by an increment on each mini batch. Yeah. All right, so, oh yeah, and hopefully it's obvious that the entire team for each project has to be in either 182 or 282A. And I'm not sure it's there yet, but we'll have a project teams folder on the Piazza soon after the lecture so you can find each other for a team. And assignment 1 is coming up soon before the project deadline, so make sure you're making good progress on that. Actually, no, I'm sorry, that's after. It's February 14, sorry. Now I'm confusing myself. 2 weeks from today, yeah, it should be after the assignment deadline for the projects. Okay. All right, so so far we've been trying to use gradient methods to minimize the loss, so we have to compute those gradients. But the networks are in general quite complicated and they've got many layers. So we want to find a reasonably efficient way of computing the gradients. So we can write down the loss as a function L of the network itself. The prediction of the network is F, and it depends on the input X and then some parameters W. And to compute the loss, you compare the prediction, F, to the actual label, or target Y. So that should be clear. So we can do that using the chain rule. It's, chain rule applies to a composition of functions. So we want to go from, let's say, loss to W. We also might sometimes want to go from loss to X, but since W are the parameters, normally that's what we want. So dL by dW in the scalar case is just dL by dF times dF by dW. Okay, should be pretty clear. So because you don't ever have really just one parameter, so W is going to be at least a vector of parameters. And in vector form, we can just basically element-wise replace dL by dW and dF by dW with gradients. Okay, so the gradient just represents the vector of all the partials of L with respect to W. And at least for the loss part of this model, our losses so far are nicely differentiable. The L2 loss for at least squares error is this nice smooth function. Hinge loss is not quite smooth, but it is, differentiable most places except at the elbow or hinge, and it doesn't matter too much what you do there. You can assign it a gradient of 0 or 1 or in between, but you have actually probability 0 of actually hitting that point. That's not quite true. It's at least mostly differentiable, and the piece that's not differentiable doesn't cause much trouble. And then cross-entropy loss applied to a logistic function turns out to have this smoothed hinge shape, which is even better and nicer than the hinge loss. So we have basically typically quite nicely behaved functions in terms of taking derivatives. So we expect this hopefully to work well. All right, so now it gets a little more complicated though in the case where this function f is itself a vector. So we might be, it might be linear regression and we're trying to predict a vector y as the target. Then we're still applying the chain rule, but now we have to consider essentially all the kinds of change that the output loss can have. Or to think of it another way, if we tweak each individual, let's see, output of f, which is an input to the loss function. So in other words, we tweak each individual tweak each individual prediction, then the net effect on the loss is going to be the sum of those. Is that intuitive? So the total change, put it another way, the total change in L is the sum of the changes in L caused by each component of f, right? L is a function of f is a vector. So the total change in L, because derivatives are linear, is the sum of the effects due to the individual components of f. Okay, so that's where that sum comes from. In other words, it's the chain rule. For each particular component of f, it's the chain rule that we just saw. Okay. So we can think of that as a matrix multiply where JL of W and JL of F are both vectors, row vectors. So in other words, J is the column index of the vector. And then, yeah, basically that the summation implements a vector times matrix multiply. Yeah, is that clear? And then also the result of that is another row vector. Okay. So in other words, well, it does turn out the backpropagation is just basically a series of these matrix multiplies. Now, okay, so I'm using this notation J. So we start with derivatives, which are scalar ratios of change. We have gradients, which is the representation for the change in an output scalar with respect to an input vector. Jacobians generalize one more step to where you have a vector input and a vector output. Okay, and so a Jacobian in general is a matrix, but because it's a superset of the gradient representation, JL of W, that's really just a gradient. We could also write it as gradient with respect to W of L, but it's a little more uniform to write everything in terms of Jacobians, where we're keeping in mind that some of those Jacobians are just vectors. In other words, gradients. Okay, so JF of W, it's a Jacobian matrix, so written out in components. There's different conventions, but you should just pick a convention and use it. You can either write it in this form where the output is the I index, or you can write it in the other form where the output is the J index. Sorry, the input is the J index. Or if you want to write it out explicitly, this is how F depends on the W weights. So there are multiple outputs, multiple inputs. They can all depend on each other. Okay. So, so a deep network, we commonly write a graphic for the network that goes from the input layer to the output loss layer. So a sequence of layers like this. Expressed though as a series of function compositions, right? The notation goes the other way. So the loss layer is actually the last function composition. It's composed with K and then through to C, B, and A. So our composition notation's kind of backwards. And we could do it either way, but we'll use a Jacobian notation that matches the function composition notation. So it's actually kind of going from output to input. Is that making sense? It's just iteratively applying the previous formula from the previous page where you derive the fact that the output Jacobian is equal to the input Jacobian times the layer Jacobian, which is a matrix. And that will have the effect when you compose it. You're basically expanding and filling in that input Jacobian. It'll sort of recursively expand towards the left. Okay, and as I said before, the Jacobian is basically a gradient. I think our gradients to this point were column vectors. For convenience, it's better if they're row vectors when they're Jacobians. Okay. All right. So, okay, so now we can express, by doing this iterative step, we can generalize and determine that the Jacobian of the loss with respect to any layer now, A, is the Jacobian of the last layer loss. with respect to its input times the product of previous layer Jacobians. Is that okay? So now we have an interesting question. We could evaluate this expression in different ways, right? Hopefully. So what people inevitably do, though, is they do backpropagation, where you start at the back end of the network, which is on the left here, and you move to the right. Okay, so why not some other order? Okay, so let's explore this, and let's try it with iClickers, hopefully. So power up if you're not already, yeah, so try the power button, and then I'm not sure if you need to hit an A the first time. It doesn't matter if you hit A and then something else. It'll record the last thing that you do. Okay, sorry. It might be rejecting you, sorry. Okay, so I think it's open now. So hopefully, does it look like it's taking your clicks?
Yeah.
All right. So, all right, and I'll read these. So why don't we do some other order other than sort of from the back of the network to the front? Could be because that's the only order that gives the correct result, or it's more efficient in terms of time. Sorry, what's that? B is more efficient in terms of time. C is left to right, avoids recomputing sub-expressions. And D is left to right, saves memory. All right. So everybody, everyone with an iClicker hopefully has answered. All right, let's see what we got. Let me see if I can get this. Okay. All right, so what did we get? So most people like C, I think. Interesting. Okay. And some people are voting E. Stop voting E, please. There's no E. So, yeah, interesting. And of course, once we show this, it biases the whole thing. But that's interesting. Okay. Oh, sorry. All right, now I have to get rid of this silly thing. All right, sorry. All right, so, sorry, let's go back. All right, so I think most people figured out this was not right. It's a composition of, it's a matrix multiplies. Matrix multiplies associative, right? So you can pick any bracketing of the long matrix product expression, and it's still going to give you the same answer. So that's not right. Come on. Left to right. Yes, left to right is more efficient by, basically an order of magnitude or a factor of n. So we'll see, we'll sort of explore that a little bit more in the moment. C though, come on. C though is also right. Left to right ordering does avoid recomputing sub-expressions. And come on. Left to right does also save memory because the more efficient operations that you do when you go from back to front also save memory. So all the last three, only one of those was actually not correct. So, so the picture, by the way, should look like this. So the shape of those rectangles encodes the dimensions of the matrix, okay? So the output Jacobian is always, assuming the loss is a scalar, which it almost always is, the output Jacobian is a vector because the first dimension has to be 1 because the output is one-dimensional. Every other dimension is the dimension of an intermediate layer of the network, and those are usually quite high-dimensional. So the product that you're computing starts with a vector and then has generally pretty big matrices everywhere else, including the input. The input is the size of the X input. So if you multiply from left to right, which remember is the backward of the network, each time you multiply, it's actually a matrix vector product, which has roughly quadratic. If everything was the same size, that only takes n squared storage. And also the temporary storage that you need is just linear, it's just a vector. So you can keep going. Each time it's like a quadratic operation. So it's about as efficient as it can be. And you never had to do any matrix-matrix multiplies. Everything was always by a vector. You end up with the gradient of the input, the loss with respect to the input. Okay, is that clear? Yeah, so we could do it a different way. Like we could invent forward propagation, short for forward propagation. So we could do it the other way. If we did that, we'd be reducing from right to left. And the next product would be another big matrix, and it would cost us about n cubed, and treating everything as the same size. Would take us about n cubed time, and also we'd have a bigger intermediate result. All right. We don't actually want to do that. It's a terrible idea, but it's a good idea for the wastebasket, and as Einstein always said, physicist's greatest tool is his wastebasket. So the more terrible ideas you can throw in there, generally the more good ones you have. So we came up with a terrible idea, but presumably people explored this a bit, and then they realized that backpropagation was a good idea. Okay. Yeah, so common subexpressions. If we think about building this, fairly simple but representative network that's got some affine layers and nonlinearities and a loss layer, then if we do backpropagation, so the orange layers are the activation layers going forward. Normally they're computed forward. Pink are the corresponding gradients of the loss with respect to that variable. And I'm using the Jacobian notation. As we go backwards, whenever you have a matrix multiply layer or another kind of model layer, weight layer, the backpropagation goes two ways. Right? You have to both compute the input activation gradient, but also the gradients of the loss. The gradients of the weights that are associated with that layer. So that's going up. Okay, and so on. But basically, you end up computing all of the pink gradient values once, or Jacobian values once. If I did it the other way, whoops. Yeah, so going backwards, you would compute everything once. If you think about trying to go forwards, I didn't really animate this, but if you went instead forwards, you'd have to go forwards for the X or the activation layers, and then you'd somehow have to go forward as well separately for the weight layers, and you'd tend to be repeatedly computing the same expressions. So common subexpressions are another weakness of not doing backpropagation. And finally, because the intermediate results are bigger, if you do something other than backpropagation, the space is also larger. Okay. So let's move on to some recipes for backpropagation. I'm going to try to do these a little bit abstractly and then do a very explicit formula that's a bit tedious, but more or less error-proof, I think. So if we have a cross-entropy loss, we write it as L equals the minus log of the X value. X is the value coming into the loss layer. So it would probably be a softmax, but we don't need to care where it comes from. And it's written this way, log of X sub Y, where Y is the index of the correct label. We could have alternatively written that as L equals Y times, or Y transpose log X, where we understood that Y to be a one hot vector with just a 1 in the position of the correct weight. But here we're just using a different shorthand. Hopefully it's still clear. Y is just the index. So there's only one term in that loss that's not 0. All right, so the Jacobian with respect to x, it's a vector, so we, for simplicity, can write down its ith component. It's also a gradient of the loss with respect to x. It's the ith component of that. So let's see. So remember the expression above. The loss is either log of x for the x that happens to be in the correct label position, or it's just 0. I mean, there's just no value there. So along that vector, the only position where you actually have to differentiate is the position xi where I equals y. Okay, that's the only term that's not vanishing. In other words, you have a 0. And the 1 over x is just the derivative of log x. Okay. All right. And more generally, this is the more general form. So now we assume y is a more general vector. It can be one hot, or it could also be a different type of basically probability vector, though. It should still have the property that the sum of its components is 1. And in that case, the formula is, only slightly more complicated. Y just acts as a linear scale factor for all the terms in x. Is that clear? Yeah. All right, so cross entropy loss is pretty easy. SVM, oh, I've got the multi-class version. Okay, should have really left this out. Might just skip through this because we didn't really do that actually. The softmax or multi-class logistic function is very important, so we'll look at this one. This one can be very tedious or relatively easy depending on how you approach it. It's a very good idea to kind of use a summary of the form of the expression. So here what I've done is said that yi is f over g, where f is the numerator and g is the denominator. Probably would have been a good idea to actually say f sub I to make it more explicit that f does depend on I. But anyway, still technically correct. Because it's f over g, it's you have to use the quotient rule. So quotient rule down there gives you, this is just out of a textbook. When you do differentiate, it's basically df over g by dxj. The top term f is only non-zero when the xj that you're differentiating with respect to is equal to I. So that's what this delta ij is. It says this term is non-zero. It's equal to 1 if and only if I equals j. That's what delta ij does. Otherwise, we're just plugging in from here. We're just substituting for the derivative of f, which is x by. Derivative is just the same function. So that's how we get this first term. And the second term, we're just taking the derivative of the bottom, g, with respect to xj, and that just pulls out the xj exponent. So, and you just multiply by f. So this is the expression. And you can simplify it still further, noticing that, that f over g is equal to yi. So just do that substitution. It conveniently comes down to this. So it's a very simple expression in terms of the forward computed yi and yj's. And that's often the case with backprop. For a lot of complicated functions, they're simple if you express them in terms of the activations of the output. Well, okay, so this is explicitly in indices. It's fairly easy to keep track of this. This is perhaps a little more complicated, but it's really just this expression and written out in matrix notation. Well, matrix notation including this kind of non-matrix operation, which is just the element-wise product. All right. Okay. And ReLU is really pretty simple. So let's see, all the functions so far are very simple because it turns out the outputs only depend on the corresponding position of the input. So, and rel u, so yeah, you can see it exactly here. The output gradient, yeah, or the component of the output Jacobian is only non-zero if it's both on the diagonal of the Jacobian. In other words, we're looking at the change in an input position that is the same as the output position. And in addition, the activation x, the input x is positive. If x is not positive, the gradient of this is 0 because it's sort of being masked out by the max. So again, taking the element-wise expression and turning it into a matrix operation, it looks like this. So that gives you, once again, a matrix that you can, all of these are giving you the matrix that then you can compose with the other matrices using backprop. All right, and there's stuff you can do. You can save some storage with rel u because, let's see, it's in the same storage. Yeah, you can use the same space for x and y, so right over the input with the output, because it turns out y is non-zero if and only if x is non-zero, so you can still evaluate this with the output only. That's called in-place rel u. Okay, now things are going to get a little bit more tricky, because now if we have a matrix multiplier or affine layer, or also called a fully connected layer, there are two complexities here. One of them is that now yi really does depend on xj for any j. And secondly, really this layer has two inputs, right? It has the x activation coming in, and it also has the w coming in as another kind of input. So let's see. So yeah, so the Jacobian with respect to y of x, that's differentiating yi with respect to xj. That's pretty simple, right? You can perform that operation on the sum, and you find that there's exactly one term that depends in yi that depends on xj. So in other words, you're fixing the j in the sum, which gives you just a single term, and it's just wij. So the Jacobian, taking that element-wise form and turning it into a Jacobian matrix again, JL of x is JL of y times w. Yeah. Okay, but now we would also like to compute the set of derivatives of yi, the output with respect to the weights. But the weights already have two indices because they're a matrix. So that thing is actually colloquially called a tensor. It's really an ND array, 3D array. And fortunately, though, we don't really need all three indices, because if you look carefully, that's going to be 0 unless I equals j. So in other words, y doesn't depend on, let's see, how do I want to say this? So yeah, the output y only depends on the w's where the first index of w is I. So in fact, it ends up only having really two indices. But still, it's still complicated because we've so far only had inputs that were vectors, and now this wij, it's an input, but it also has two dimensions. We can still crank it through. Yeah, so it ends up having this form. And when we write out the Jacobian of w, you can actually write it in this form. In index form, it's shown in the line above, this line here. Okay, we do the same thing we had before. The only difference here is that now instead of a vector of inputs, we've got a matrix of inputs. The output now, what we end up doing now is multiplying a column vector by a row vector. It's a little strange. And that's going to give us actually a matrix of the correct dimensions for the Jacobian of w. we're being a little bit sneaky here because the lost Jacobians so far have all been vectors. It happens that we can make the lost Jacobian here basically output a matrix that matches the dimensions of W. It can get very confusing, but just keep looking at the formula in terms of indices. And then when you're ready, collect the constituents of this expression together to make a matrix expression. All right, so this is almost always going to be very confusing, this slide. If you're not confused, come back and read it again. I think it'll work at confusing you. So what I'm going to try to do is just do it a couple of times again, and hopefully it'll become less confusing. All right, so we did something kind of non-standard and sneaky here. We managed to compose the Jacobians. Notice that the JL of y, for instance, we transposed that. It normally has just been a row vector, and we turned it into a column vector. We did that because we actually, it ends up matching the row indices of the JL of W on the left. So we've kind of changed the dimensions of everything around to make things come out as a matrix, as a Jacobian of a matrix that has the dimensions of W. So we can, it's basically a gradient in matrix form that we can then just add later on to W. All right, so if we just go back to the expression that we just did in element-wise form, we took a derivative with respect to a matrix now of weights instead of a vector of activations. But the chain rule tells us that as long as this bottom thing matches the denominator of the right-hand side of the chain rule expression, we're OK. Okay. The other index, J, J is basically the dimensions of the sort of hidden layer between W and L, right? There's that Y layer in there. All we have to do is match the indices, sort of, let's see, the Jacobian indices in the first term in that expression and the Jacobian indices in the nominator of the matrix Jacobian, so that matrix product still works, and also match the indices of the sum. So, because in other words, we're just trying to make the chain rule work. Chain rule works if those things all match there. Okay. So we can take that explicit formula and kind of repeat what we just did. Notice that the most complicated Jacobian on the right side, which is really a three-dimensional ND array, is mostly 0, so we can reduce it, in fact, to a normal matrix. Well, in fact, I'm sorry, yes, we can reduce it to a matrix which actually happens to evaluate to a vector with broadcast. Broadcast's not shown there, but it does equate to a broadcast. And then plugging that in gives us the final expression for the gradient with respect to W of the loss in components, and then it's still the same matrix form. Okay, so we can generalize that a little bit more, and then we can pretty much do any back propagation for any dimensional input or output, okay? So in the very general case, we have a layer that has an output Y and an input X, and I'm only showing 2 indices for each one, but it could be 4 or 5 or 3 or 2. It could be any number of indices. So where you see IJ, just extrapolate that to IJ, K, L, M, however many you need for that particular layer. And the same thing for Y. We'll assume that MN is really shorthand for MNOP, however many are needed. So then the input Jacobian that you want to compute is DL by dx, ij, k, etc. And the output Jacobian, which is the input to this calculation, is dl by dw, by dy, MNOP, etc. And so you should be able to see it's the same form as the previous one, just with extra indices now for the kind of hidden layer y. Is that clear? And now your summation is over however many internal dimensions you have for y, because all of them represent paths where gradient can propagate from the x layer out to the loss layer. So all of them are, have to be included in the sum. So yeah, and we'll see in a second that it actually almost all the time you do have layers with higher numbers of dimensions. Yes, but without sort of trying to do another possible example, the general principle is, plug in the expressions. You should be able to compute these expressions in most cases, or to be a bit more explicit, that orange expression there is actually the input to backpropagation from the next layer. If you write a function to do a backpropagation for a given layer, the dl by dy is actually, literally an input vector or matrix or tensor, right? It's just the argument to your function. So you can just treat that as symbolic. And then what you have to compute is the result of that sum multiplied by the appropriate partial derivatives of y with respect to x. And again, without going into gory details for all the examples, that dy by dx is very often, or almost inevitably, sparse. So you almost never need to compute with all of the potential dimensions. So we just saw for the affine layer, you've got 3 potential dimensions, but it's actually 2-dimensional. And for convolution, it also looks like it could be 8-dimensional, but it's really 4-dimensional. So these expressions end up being a lot simpler. Hopefully, if you compute them explicitly using the sum notation, because that's everything here is really a scalar plus some summation over the appropriate set of terms. You don't have to think in terms of vectors and matrices until you finish computing the expressions, and then you can collect together the terms and rebuild it as a matrix expression or a convolution operation. So this is a bit abstract, but hopefully it'll help. Is it somewhat clear why we're doing this? You can still think of x and y as vectors where the multiple indices is just sort of a convenience to represent the vector in a kind of a compactor form. It's really otherwise just the normal chain rule. All right. So anyway, any questions? I should have waited before skipping. So it's probably still somewhat unclear, but once you do the homework, I think hopefully it'll be more clear. And look at this. So yeah, deep networks often have higher dimensional activations and higher dimensional gradients. And that's natural because of what they're representing. In particular, most networks use mini-batching, so that, let's say, even if you have a time series with 10,000 time steps, a mini-batch of 32, your actual input is a matrix of dimension 10,000 by 32. So you'll have that extra index for the sample inside the mini-batch to carry through the calculation. Yeah, so deep learning toolkits inevitably have data structure support for tensors. They've unfortunately been called tensors, and they're not tensors mathematically because tensors have extra invariances that random high-dimensional matrices don't have, but the name has stuck. So for instance, if we have image-based networks, those commonly have 4-dimensional activations. 2 of the dimensions are the spatial dimensions, width and height. So you'd expect those. It's convenient to organize an image as not just as a big vector, but as an x, y array. But in addition, there's this dimension C. In the first image, it encodes color, but in subsequent images, it encodes different filters looking at the same input. And then you have, in addition, a mini-batch dimension. So the common representations for image-based ND arrays or tensors have these 4 indices. And in Python or other toolkits, they can be ordered in one of 2 common conventions. And probably NCHW is now pretty close to universal because it's supported. It generally gives a little bit faster results on NVIDIA GPUs. And this one was a bit older, probably still supported in the toolkit, but a little bit risky to use because it's not supported everywhere. Yeah?
Is NCHW faster because of prefetch considerations or just?
It's most likely to be locality related. Let's see. Well, that digs very deeply into the implementation, which we were just going to briefly describe at the end of this lecture. There are probably at least a half dozen different implementations of convolution in the NVIDIA software right now, and I believe most of them are faster with NCHW, but the reasons are really complicated. So it's best to defer that discussion. So convolutional networks are commonly drawn this way. And so you see 3 of the dimensions. Each block is a set of features. There's C features in this layer. And the spatial dimensions are also shown. And what you can see is, starting from the image, which is, 224 by 224 by 3. So the 3 is the color dimension. You go to a first hidden layer, which has 96 features, and drops the resolution spatially down by 4 to 55 by 55. And then you commonly step down in space and increase in number of filters. But you're typically overall at the steps reducing the number of activations because that compression actually helps the representation. There's always going to be a mini-batch dimension, but because the mini-batch dimension is this, first of all, it's going to be the same for every layer, and second of all, it's often variable, independent of everything else. You might find that the 32 or 128 gives best performance. Generally, bigger values are better for performance, but they also use a lot of memory. So it's really an independent parameter that's usually not shown. And then, so these are the activations. And between the activations are the actual convolutional filters, which we'll talk about shortly. But that's hopefully a good rationale why we want higher dimensional arrays. And when we actually do backprop, we want to sort of keep track of more than just a vector index. All right. Last point to make about backpropagation is that there are 2 sort of distinctive kinds of derivative that we do generally. One of them is called a data path, where you're going back from the activation in this layer to the activation in the previous layer. And a model path, which means we're going from the output of this layer to the weights that are causing that output, the parameters of a convolution or a affine layer. And that's called the model path. And the toolkits inevitably can include 2 different sets of functions for computing these different things. And they may even run different algorithms that are optimized for that task or the other. And yes, and another interesting point is that the blocks in the data path have a mini-batch index, right? Because they represent individual samples. The data path tensors or ND arrays don't have a mini-batch dimension. That should be hopefully intuitive, right? Because they're the dimensions are the model parameters. Doesn't matter how many samples you have in a mini batch, your gradients are the same size. So, all right, it turns out it sounds complicated, but it just works most of the time. Even in terms of when you work out what these matrix expressions look like, or the convolution expressions, this aspect seems to take care of itself. Okay, so a quick summary of backpropagation. Well, we didn't even really talk about this, but you compute activations forward from the front of the network to the back, because at each step you need the activation from the previous layer in order to compute the activation at the current layer. So that's hopefully obvious. The derivatives, on the other hand, we compute normally from the output back to the input. And we don't really have to do that. It's a performance or a convenience issue mostly. We could do it in a different order, but it would just be much more expensive. All right. So any questions before we leave backpropagation? No? Okay. One last look. All right. Okay. Well, so let's look at convolutional networks as the first really interesting and high-performing example of deep networks. So there's some input layer, which will be either an image or a mini batch of images, various hidden layers, and then an output, which is typically either a prediction or maybe the loss on a prediction, depending on how you want to finish the network. So we already looked at affine or fully connected layers. They allow you to mix contributions from any input element to an output element. But for images, because they're already huge, it's impractical to have fully connected layers, fully connected linear layers from an input to an output. If you work it out for AlexNet or a similar network, you'll find that you'll have billions of parameters. So people don't do that. Instead, they do convolution. Convolution intuitively is a filtering operation, or it's like sliding a weighted window over the image, and does a variety of things, including computing approximate gradients, curvatures, more complicated patterns are recognizable. But you can just see an example here. So there's a set of weights in that small matrix called the filter, and then you don't really see the weights, but you can imagine the intensities of the pixels from, say, 0 to 255, with white being 255. So that image there is an implicit matrix. And then the output, it's written typically as H star F. Star represents a convolution operation. Both the output and the input image have, let's say, x, y coordinates, or height, width coordinates. The convolution is defined by taking a sum of products where you consider the possible displacements I and j from the center of the filter, and you basically move either the filter or the image by those displacements. And you have to move them in opposite, I'm sorry, not either or. You move both of them by the displacements, with the filter and the image moving in opposite directions. So in other words, H is here the filter, and F is the image. And you can see that we use positive indices for the filter, and then negative indices for the image. All right, the negation is very important for a lot of the properties of convolution, but people are very sloppy about actually including them. So you have to be careful about what is actually being done in the toolkit. Get to that in a moment. Yeah, so if that is a convolutional filter, I don't literally take that filter and apply it and shift it over the image. I have to flip it over in x and y first because of the negative indices. So if you look at the image-based representation, you see it's white on the left side and black on the right side. So the white encodes the plus ones and the black encodes the minus ones. So that's the filter that it's actually being slid over there. If you want to think of it as sliding that set of weights and applying them, that sort of smaller image shows what the filter weights look like as they're being slid around. Yeah?
Just to clarify, is F a filter?
No, F in this case, yeah, the thing is they're interchangeable. So it made more sense, yeah. Yeah, the way, yes, this is saying it's the filter. Yeah. Formally, yeah, all right, just consider F to be the filter. It's very weird because most of the coefficients of F are 0 when you do that. It's more convenient, really, to have H be the filter and then the indices I and J range from 1 to 3. But either method is correct. It's just that if you cause F to be the filter, you'll have to sum over infinite indices. Is that making sense? It's a little bit awkward either way, so this might have been the more awkward of the two choices, but it's still correct. Okay, so there's the convolution formula. It's commutative, so H star F is equal to F star H. You can do some substitution of indices to make that work. And yeah, because of that, so here I've made H explicitly a finite filter, and I've made its indices range over the size of the filter. Yeah, so yeah, so hopefully that's intuitive why you can do this. If H is just 0 outside of that range, that will work. Okay, convolution looks a lot like correlation. The correlation is almost the same formula, except the indices are used in one function and then added to the other one. So whereas for convolution we had minuses here, correlation looks like this. So it most of the time doesn't matter if you use one toolkit for both training and testing. It'll use that representation all the time. But be careful if you try to transfer models from one toolkit to the other, or if you change the parameter inside the model, because there is typically a parameter that's settable that says within a convolution operation that says this convolution is either a convolution or a correlation. So convolution is really the umbrella for both terms. Okay, so just be a little bit careful about that. It's good to sort of inspect and make sure you know what things are happening. For instance, the convolutional filters in the assignment are actually correlation filters. All right, so far so good? Okay. All right, so let's do a little bit more filtering. So the array/image on the left shows a set of explicit pixel values in a square array, and the intensities are meant to suggest the corresponding values. So 90 is fairly bright and 0 is dark. And the filter that we're applying is the symmetric filter, so it's actually going to hide any nastiness to do with convolution versus correlation, because it won't matter. But we're going to apply that filter to get an output G. So the red square on the left is the kind of support support of the filter, meaning where the filter is being applied in the image. So there it really just is an average of the values. And as we slide it to the right, now it's an average of 90 and a bunch of zeros. So it comes out to be 10. And as you move to the right, it increases and then stabilizes, and then eventually will be going down. So what should this value be, for instance? Anyone? Well, in case you didn't notice, it's an average, but it's also you can do the sum and then divide by 9. Yeah?
It's 15.
Yeah, it's just 50 because it's basically counting the pixels underneath because everything's the same brightness. Number of white pixels. What's that one then? 90, yeah. All right, so and so if you both fill in the values and then apply appropriate colors, corresponding colors, grayscale, on the right you get this thing. So you can see, compared to the image, this filter is applied a blurring operation, right? Because, well, hopefully it's intuitive that blurring kind of bleeds color and intensity from the left and the right, which a local average like this does, and produces a blurrier result. But some other filters will sharpen, as the one we just saw. It also sharpens the image. Okay, so what would this filter do? We kind of just looked at it. What do you expect the output to look like? A blurry eye, right? Yeah, it's like a morning eye, or pre-coffee eye. What about this one? Yeah, it's identity. All right, let's do one that's slightly hard. So convolution with this filter, what is that going to do? So I guess eye clicker again, eye clicker time. Oops, okay. All right, this is a good test of whether convolution is really understood yet. All right, most people think C. It's good that some people really like E again. That's very interesting. Or there's some problems with the eye clickers. I don't know. E is beating D. Oh well, and A, I think. All right, so let's close that and move that back. All right. So yes, blurred horizontally is not happening because it's just a single pixel, so can't blur. Shifted one pixel to the right is the correct answer, B. Remember, you have to flip the filter for convolution, and when you move that, so in other words, the center pixel is copying from the left. Center pixel is copying from the left, which means it's moving the image to the right. Okay, and so as you can imagine, this would be correct if either the one was on the other side or if that was a correlation filter, not a convolution filter. And last one is nonsense, of course. I guess I should figure out what option E was for next time. So an interesting property of convolution and not correlation is that if one of therefore G is the identity, so the identity here is a 1 and all zeros, right? Because when you have 1 and all zeros, it copies the other thing. Which means if you have a 1 now in the image instead of the filter, it'll produce an image which is a copy of the filter in the middle. Is that making sense? If this was a correlation filter, the copy would be flipped. So one way, if you want to check what you have, you can try filtering, set it up with this filter and that kind of filter and then an image to see what it does. Okay. Yeah, and so you would also get that result if you had that kind of correlation mask. All right, so another high-level question. If we have this set of filters along the top here, and the images on the right there, can you figure out of 1, 2, and 3? So each one of 1, 2, or 3 is the sort of average activation of the filter above it to one of the images. So in other words, each one of 1, 2, and 3 goes with either A, B, or C. It's a matching problem. And the columns our corresponding filter output. So for instance, well, let's see. Let's pick an easy one, B. So it's got mostly vertical kind of energy or gradients, right? Oh, well, no, that's not a good way to say it. It's got, the gradients are actually horizontal. So which of the filters would respond mostly to B if you sort of go across from left to right? So it's sort of the middle one, right? So for B, you would expect the middle filter to have the strongest response, right? So which of the rows has the strongest response at B? Number 1, yeah. So you'd expect 1 to go with B. What about A? Thoughts about A? Which filter would respond the strongest to A? The third one, maybe. I would guess either the last one or maybe the fifth one, because if the image has a lot of stuff oriented in a certain direction, oriented meaning invariant, then its gradients are going orthogonal, and you want a filter that's gradients are going orthogonal. So I think 5 might be the strongest there. But basically 5 and the last one, can we see? Well, interestingly, well, I think for A, I would just go with the last filter because it seems to be filtering for blobs. And that would suggest that 3 is the one that goes with A. But surprisingly, it is surprising because the fifth filter didn't respond very much. Instead, the first one did. Bit of a paradox. Well, all right, I'll let you mull that over, actually. I think the authors of that slide didn't want to reveal the answer. All right, so maybe just using inspiration from these filter examples, we could, at this point, do one of two things. We could build convolutional layers or image processing layers where each output active cell looks just at a little window, but they still have independent weights. Sometimes people have actually used those kind of layers, not very often. They're still very expensive because, so here what this is saying, that each filter has its own weights. Each filter is or the cell in a different position has a different filter. And that's probably overkill. That would be 4 million parameters. But there are examples where this does help. For instance, where you have images that are not really shift invariant. You know, they're, for instance, centered face images. The features tend to be different in different positions. But apart from that, people don't use it. Mostly, you want the filters in different positions on the output to be the same weights, which are convolutional filters. And let's see. We should go down. Oh, that's weird. All right. No, that looks not quite right. Filter size, 4 million parameters. Well, all right, I know what happened there. Should have been a lot less. I'll double check that. Anyway, no, that in practice what people do is use convolutional filters, meaning the weights are the same in different positions of the output, but they're still learned. Okay. Yeah, now, all right, this for some reason shows the actual shared parameters. Okay, so it's 2 orders of magnitude, no, 3 orders of magnitude less. Okay. And here are some typical filters that are actually being learned. And what this is, each picture there is a visualization of the set of weights of the filter. And there are multiple filters being applied to each position. And that's going to be clearer in a second. Okay. So actually, let me not skip ahead too fast. Are we clear so far? We've decided to commit to filters that have the same weights in each position of the output and multiple filters. So now let's look at some of the counting of degrees of freedom. So if we have a simple image, 32 by 32, and 3 colors, and we apply a small 5 by 5 filter, it has to be 5 by 5 by 3, right? Because it has to apply a weight to each color. So that 3 has to match the last dimension of the image. Okay, so that's what that's saying. Now, what's the output size? Well, we'll get to that in a sec, actually. So this is kind of a linear operation. And because it's a linear operation, it typically also has an output bias, B. And the output bias is going to be, well, here it's just going to be a constant. When we add multiple filters, it'll be the number of filters. So anyway, again, if you take the weights, we're thinking about applying a corresponding weight to a pixel of an image and then taking the sum. So it's a weighted sum of the inputs under the filter. And yeah, so you can think of it as the weights as being linearized to a vector and the little square window being linearized to another vector x. It's just that weighted operation. It's obviously more complicated because there are extra indices, but let's not do that just yet. All right. So for one pixel, we've got to sum over every input position under the filter. And then we've got to slide this window around across the input image. And I guess we skipped ahead a little bit, but if you figure out how many positions will actually fit, it'll, in this case, be the dimensions of the input minus the filter dimensions plus 1. So yeah, so that ends up being 28 by 28. And we're only applying one filter so far, so the depth of this next layer is 1. But we could do more. We could have another filter with different learn weights and produce another output layer with the same dimension. And that's what's always done. And rather than doing separate operations, these are all bundled up into a higher dimensional operation where the filter now is really a vector of filters. And then the output will have some new dimension, which is the number of filters. OK. So if you're keeping track, the dimension of this sort of more general filter now is 4, because it has height and a width. It has an input number of channels that matches the input depth of the input activation layer, and it also has an output channel depth, which is going to create an output of that dimension. Is that clear? So yeah, so these are 4D tensors or ND arrays. Okay, and then the somewhat higher level picture is that we intersperse those convolutions with nonlinear operations, mostly ReLU. The ReLUs then allow the network to compute nonlinear functions, if you want to think of it as kind of piecewise functions, piecewise linear functions. That sounds limiting, but actually piecewise linear functions can approximate any shape, and they do a very good job of it. Yeah?
The convolutions followed by the ReLU function, is that different from, I'm sure you're going to talk about it later, but the convolution followed by the max pool?
Yeah, pool is coming up in a few slides. Well, pooling's not being used as much as it was in the past because the networks have gotten a lot deeper, and what pooling used to do was quickly allow you to combine effects from different locations. Now the networks are so deep that happens anyway, so people don't use pooling much anymore. But we can keep iterating. You know, now that output image from the first step now looks like an input image. It's still three-dimensional, so we can just do the same thing. And our image is sort of shrinking a little bit each time, but still not too bad. It is getting thicker, though, at the same time. We're adding more filters in general. And if you do that, you get this remarkable effect that we have kind of summarized in the first lecture, which is as you go from the input image to the early hidden layers and then to later hidden layers, well, the features that they're responding to, let me make sure I know what's, yeah, right, this is the, all right, yeah, these are actually sort of recursively computed activations. But just think of them as visualizations of what the different filters respond to. They're color sensitive, some are edge sensitive, but very low level in the beginning. But then as you go up, they become much more complicated and they start responding to wheels or circles or eyes or even animals and faces. So somehow the functions that they're learning are obviously quite complicated and nonlinear. All right, let's see, where are we? Yes, well, I think we summarized this a bit already in the first lecture, so we're running out of time, so I'll keep going. Actually, all right, so let's do one more thing, which is looking at striding, which is a way of reducing more aggressively the size of the image. So when you have a filter that's fairly large that looks at an area of the image, if you take that filter and slide it by 1 pixel, the new output is quite similar to the previous pixel output or previous position output, right? You've only slightly moved the filter. So there's a lot of redundancy when that happens. That generally doesn't make it a good representation. So it's typically desirable to slide these filters, at least in many cases, more than 1 pixel. So let's look at the 1 pixel case first. And as we said before, you can slide basically input dimension minus filter dimension plus 1. And in this case, 7 minus 3 plus 1 gives you 5. And though, because we do want more independent outputs usually, we could instead slide by 2. And how big is the output? Sorry, it came up too fast. 3 by 3. All right, so we only get 3 output positions, but they're now more independent of each other. And that's typically a good thing. All right. Yeah, let's see. Yeah, if we tried to do stride 3, it would be messy because we could do the first step, but then the second one wouldn't fit. Okay. So in general, the formula for the output size is a function of the input size n and the filter size f is n minus f divided by stride plus 1. And in nice cases, that will come out to an integer, but not always. So, and here there's a slight difference. Oh yeah, let's do padding first. If you have a very deep network, like a residual network, which has 50 or 100 or 200 layers, you know, hopefully by now you've seen that if we just keep applying even 3 by 3 filters, the size of the image will shrink by 2 pixels each time. So that's not good. You have hundreds of layers, you'll have nothing left. So instead, a common practice is to pad, just add zeros around the edges of the image of the input, such that the output typically ends up having the same size as the input. In this example, it doesn't quite do that. Oh, no, yes, it does. Sorry. Yeah, if you have a 3 by 3 filter and you add 1 row of zeros and column of zeros around the image, the output will be the same size as the input, right? Yeah. Yeah, so you conserve the size of the output. But it is very important if you do this to make sure that the non-zero input image is still mean 0. In other words, that having a 0 value isn't really unusual relative to the actual activations. If you took a raw image, and you do this directly to a raw image, you'll get bad results because it's really like putting a black frame or house or something around the actual image. It really confused the network. So normally, at the beginning of a network, it's very normal anyway to just subtract the mean for those pixels, for each pixel position, and that causes the activations of the input image to be 0 on average. And then padding is benign in that case. All right, so we've got still a few slides left, so we'll roll those over to next time, since convolution is still the main topic for next time. And otherwise, yeah, we'll see you next time.
I actually forgot to buy an iCloud. Can I email you with my name? For attendance purposes?
Okay, yeah,